Alright, hello everybody. It's me from the future, just here to say that I actually do solve both problem A and problem B, not just problem A. So, contrary to what I say at the start of the video, I will be covering both of them. So if that's what you guys are interested, keep watching. Hope you guys enjoy the video. Okay, so this is problem A maxima from the Codeforces Global Round 23, which is contest 1746. This contest completed really recently, so I'm gonna reveal my solutions to some of the problems, and this video is gonna cover problem A. Okay, so here we go. It says you have an array A of size n, consisting only of zeros and 1, and an integer k. In one operation, you can do one of the following. Select two consecutive elements of A and replace them with their minimum. Or select k consecutive elements of A and replace them with their maximum. So each test contains multiple test cases, etc., etc. And we want to check if it's possible to turn A into 1. Let's see here. We know that k is less than n, and we've got some values, and we want to see if we can turn A into 1. So let's see how we do that. So suppose I had 0, 1, 1, 0, and 0, right? Something like that. And I could take a group of 3 and turn that into a valid, or turn that into a maximum. So obviously the maximum of 0 and 1 is going to be 1. So it basically takes a group and turns it into 1 as long as there was a 1. So I'm going to take this and I can turn this into 1. So if I take all of these, this becomes 1. And that ends up with 0, 1, 1, and then I can take all of these and turn that into 1. So suppose I had a group of 3, right? And now I have a group of 3 and a 1. Now if I can get down to a group of 3 and a 1, so this currently I have a group of 5 and some 1s and some 0s. But if I can get it down, if I can somehow turn this array into an array of size 3 of like 0, 0, 1, or maybe something else, essentially an array of size 3 with exactly, or with at least 1, 1, right? So if I can turn this into an array of size k when we generalize, and this would be n, consisting of some values with a 1, then I'm good to go, right? Because then I can just apply the operation 2. So what would this look like? This would look like, well, I have 0, 1, 1, 0, 0. I could apply the minimum here and turn this into 0, 1, 0, 0. And then I could apply the minimum here and turn this into 0, 1, 0. Now I have a group of 3 with 1, 1. That's at least 1, 1. And so I can take this entire group and turn that into a 1. So if we can do that, if we can go from this step right here to this step right here, and let me start using some different colors. If we can go from this step to this step, then we can easily just finish off, right? But how can we do that? Well, I'm going to argue that as long as we have 1, 1, we can do it. Always. So let's take a look. Suppose I had some zeros, some 1s, some 0s, etc., etc. And for the time being, suppose I had a group of some zeros, exactly 1, 1, and a group of another set of zeros, right? And there's exactly 1, 1. Suppose this is size k, so size n. I could apply a minimum operation here, turn this into 0, a minimum operation here, turn that into 0, minimum operation, turn it into 0, into 0, into 0, into 0, as much as I needed to shrink it down to size k. I could do the same thing here. So essentially, if I had 0, 0, 0, 0, 0, 1, 0, 0, and I needed to shrink it down to a size of 4, I could get rid of this, this, and this, and I'd end up with the size 4. So what I'm trying to say here is I can apply some operations to keep a 1. So I just keep applying minimum operations while making sure I still have exactly 1 left. And I can do this because k is less than or equal to n, and is less than or equal to 2. So obviously I can, wrong statement. 2, we do operations of 2, and we're always going to have at least 2 because we're going to finish off with k. So we can do it. So just as a walkthrough, what would this look like? This would look like for this test case right here. I would have 0, 0, 1, 0, 0, 1, and I need to end up with 3. So let's say I'm going to keep this one right here. Let's say this is the one that I keep. Then I can take this group of 2 and knock off u, I can take this group of 2 and knock off u, and I can take this group of 2 and knock off u, and now suddenly I have 3 left. Voila. Now if k was 2, what could I do? If k was 2 and I needed to do this, well, at this point I can just do the maximum operation on this set to get a 1, and then on these two to get a 1, right? So if k is 2, that's pretty irrelevant, because then we can just max out everything. But if k is not 2, then this is our strategy. So ultimately, as long as we have a single 1, we're good. So we'll start off with, and now we're going to take in n and k, right? And we have a vector of int v, array of size n, and then 4 int and I in v sim I. Now what we can do is we can check, do we have at least one 1? So I can say bool or int c1 is equal to 0. Or actually we could just do c. For int I in v, c plus equals I. And now, if c is greater than 0, then we had at least one 1, so we can sell yes. And otherwise, no. So let's test this out. So we'll go to a custom invocation, copy this, and run. And yes, 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 no, yes, yes, yes. Perfect. So now let's submit. And accepted. Perfect. Let's move on to problem B. So, problem B states, you have an array A of size n consisting only of zeros and ones. You can do the following operation. Choose two indices I and j, add ai to aj, remove ai from aj. Note that the elements of A can become bigger than 1 after performing some operations. Also note that n becomes 1 less after the operation. What is the minimum number of operations needed to make A non-decreasing, i.e. that each element is not less than the previous element? This problem is a little bit more tricky, and the reason it's more tricky, but it's much, much faster to get. So let's take a look. So suppose that we had an array like this, 1, 1, 0, 0, 1, 1, 0. What we want to do, essentially what this problem allows us to do, is take this value, this 1, and push it and swap it with a 0. Essentially we can choose a 1 and a 0 and swap the two values. Now really we never want to have a value more than 1, because that just makes it more hassle for us to check, is that non-decreasing, because now we have multiple values to check, and that's just annoying to deal with. So we want to keep it so that we always have 1s and 0s and no more and no less. And in fact, there's a long proof that that's optimal, but I'll leave it to your intuition to figure out why it makes sense that you would really never want to add. Like if I added this 1 to here, that would give a 2, and that would give so many problems. Like if I added this 1 here, well now I don't just have to worry about the 0, I also got to worry about this 1. So we always want to add to zeros. But now, which 0 do I add to? And more specifically, in the context of this problem, when we add ai to aj and remove ai from A, when we add ai to aj and remove ai from A, what we're doing is we're essentially taking this out and erasing this with 1. But in the context of our problem, when we do it with zeros, we're actually swapping them, because we know that the zeros have to be at the start. So we can consider it as swapping. And now the question is, what's the minimum number of swaps that are needed? This problem becomes really, really simple. Like, what's the minimum swaps that are needed? Well, that's just simply the number of or something similar to the number of inversions. Essentially, if this 1 is before a 0, I'm going to need a swap to take it out. I'm going to need a swap to take it out. And this will be a 1. This 1's before a 0, going to need a swap to take it out. So for every 1 that's before a 0, we're going to need a swap to take it out. But there's the catch. You might be thinking, well, wouldn't that make this 4, right? Because there's 4 1s before the 0. Actually, when I take this 1 out, when I swap this 1 and this 0, right, I end up with 0, 1, 0, 0, 1, 1, 1. And there's the catch. I'm removing the ending 0. So whenever I swap, I also remove a 0 that could potentially be a problematic 0. So if I swap this 1 and this 0, I'm also removing some of the issues with this one. So what we want to do is swap the first ones with the last zeros until all the zeros are before all the ones. In this way, we can sort of ensure that we're removing all of the problematic zeros while we're removing all of the problematic ones. So we would take this 1 and we would pull it out to here and swap it with this 0. So 0, 1, 0, 0, 1, 1, 1. And yes, technically speaking, this 0 actually doesn't exist, but because it's easier to think of it as it does, I'll leave it there. And now we have this 1, and we can pull it over here to this 0, because this is now the last 0. And so what that will do is we'll take off this 1, and we'll take off this 0, and we'll end up with 0, 0, 0, 0, 1, 1, 1, 1, etc. And so we're left with this array, and now we're done. And that took a total of 2 swaps. So if we take a look here and we tried it out for this one, I'd have to take this 1 and put it here, so that's 1 swap. Take this 1 and put it here, so that's 2 swaps. Take this 1 and put it here, so that's here, so that's 3 swaps. So that would take 3 swaps, and the answer is 3. So we'll say b.cpp include bits slash std++.h using namespace std. And for simplicity, I'm just actually going to copy all of this and paste it there. But we're going to delete that. So now int n, sin n, vector of int v, array of size n, for int I in v, sin I. Now we go through and we need to push each one to the farthest back 0. So we can use a bunch of different strategies for this. We can use 2 pointers, we can use whatever we want, but really what I'm going to do is just use a queue. So I'm going to create a queue of int q for int I is equal to n minus 1, I is greater than or equal to 0, I plus plus. If v of I is equal to 0, q dot push of I. And now I'm going to go through forward for int I is equal to 0, I is less than n minus 1, because obviously the last one is good, I plus plus. Then, and actually in contest I did n minus 1, but for clarity here, we'll just go with I. We have to do something. And one more thing that I reminded of is we have to first check for this to work that we're not already non-decreasing. So let's quickly do that. Bool flag is equal to true. For int I is equal to 0, I is less than n minus 1, I plus plus. If v of I is greater than v of I plus 1, flag is equal to false. We could break, but you know it's not really necessary. If flag south yes slash n return, or south 0 actually in this case, return. There we go. So now we have asserted that it is no longer it is not non-decreasing. So basically, it is ascending, or it is not non-decreasing. So it's not ascending, right? So if v of I is equal to 1 and q dot front is greater than I, which is essentially saying we have one that is after us, we're going to swap them. So we're going to say v of I is equal to 0, v of q dot front is equal to 1, v dot pop, q dot pop. And then if q dot size, or if q dot empty, then we can break, because we are out of zeros, so we're obviously done. And so now, we just have to keep track in c is equal to 0, how many operations did we use, and let's do that here, so that way we get them all. If or rather south C/n, and we're good. Let's test it out. That's rather disappointing that Codeforces has crashed right as I was doing my video. Alright, you know what? We don't need no Codeforces. We're gonna go through terminal way. And let's copy that. Ooh, address boundary error. There we go. That's interesting. Ah, that's wrong. Let's run that. There we go. Yeah, so that's right. So now we'll submit code and submit. And it's accepted. That was problems A and B from the Codeforces Global Round 23. If you guys did enjoy, please don't forget to leave a like and subscribe. It really means a lot, and it really shows me the support that you guys give and that I should keep making videos. And with that, I'll catch you all in another video.